Welcome to Lecture 1 by Semiconductor IntellectuaPCB on solid-state electronics. Today we are going to introduce you to semiconductors and crystals and some of their interesting properties. So before indulging in the technical discussion on semiconductor technologies and crystal structures, we have a paper from Reza Turkamani from Faculty of Physics, University of Tabriz, Iran. In his paper, he explains how AG-topped zinc oxide nanoparticles modifies the structural and optical properties of semiconductors. Techniques like zinc oxide and PL techniques have shown that modified band gaps in crystals and semiconductor materials. This is why in our today's lecture we are going to start up with the crystal structures and how crystal structures are important in semiconductor applications. As we promised, now we will have an insight into research groups that are working on crystal structures and their properties today. So today we will start and share the work of Reza Turkamani. Reza Turkamani researches semiconductor nanomaterials, especially zinc oxide system. His works actually works on how crystal structures improves optical, catalytic and sensing performances of semiconductor applications, showing how material engineering and semiconductor physics is important in development of solid-state electronics and semiconductor applications in various fields. His key work is on optical properties of zinc oxide systems, specifically in bulk, nanoparticles, and nanorods. They illustrate how changes in crystal growth conditions can improve or de-improve the semiconductor performances. So we start from the question that what is a semiconductor? What are semiconductor materials and how semiconductor materials are defined? What is the basic definition of semiconductor materials? So we will start from the definition that is proposed by Streetman and Banerjee, that is mentioned in their book Solid-State Electronic Devices, that defines the semiconductor material as a material that has its electrical conductivity in between metals and insulators. One such another definition is proposed by Sedra and Smith in their book Microelectronic Circuits. They define semiconductor as the materials that have electrical conductivity in between conductors and insulators. In summary, we have seen that Banerjee and Sedra and Smith have used a very similar definition to define semiconductor materials. What is common in both definitions is electrical conductivity, metals, and insulators. So let's come and decide what is metal and what are insulators. So first of all, what is a metal? Metal are the materials that have very high electrical conductivity. So to conduct an electricity, we need to have a very less band gap between the electron shell and the conduction band. So these materials have very less excitation energy, that is around 0.1 to 0.3 electron volts, or this is also defined as energy band gap, and that will be discussed later on when we will be studying in detail about energy band gap theory, and we will also see Fermi levels over there. So normally if we define them, the materials with very high electrical conductivity, they have very much electrons that are capable of conducting enough electricity very easily, and in terms of energy band gap, they have the energy that is required for per electron to excite is around 0.1 to 0.3 volts. So this is how we define metals. So coming to some of the examples to realize what are common metals are copper, iron, zinc, silver, and gold. If we talk about insulators have very high energy requirement to excite an electron. They are the materials with very less electrical conductivity. They are commonly and can be called as that they have very high electrical resistivity. So insulators are exactly opposite of the concept of the metals. So, if we talk about electrical conductivity, and we have discussed it and we have defined insulators, so we can think about insulator examples. So, common examples are wood, plastic, fibers, and bricks are also considered the examples of common insulators in our day to day life. So, to conclude, what is a semiconductor? So, semiconductor is in between metal and non-metal. It must be having its electrical conductivity or energy band gap between 0.1 to 0.3 electron volts, up and in between the upper limit, that is 7 electron to up to infinity. So, if we conclude the energy band gap requirement for a semiconductor material is 0.3 electron volts up to commonly it is 5 electron volts, but sometimes in some cases like in gallium arsenide and gallium nitride it can exceed to 5.5 or 6 electron volts. So, starting to a new chapter, that is chapter number 1, that is Introduction to Crystal Properties and Growth of Semiconductor Materials. Coming to key topics that we are going to study in this lecture related to this chapter, that is semiconductor materials, what is crystal, and what is periodicity, and what are cubic or diamond structures, that we are going to see in our upcoming lectures as well. The key questions will be what is meaning of crystals, what is lattices, and what is periodic arrangement, and order in solid state materials, specifically orderly structuring of solid state materials. Semiconductors like silicon, gallium, indium phosphate, and arsenic have uh, band gaps between 0. 0.3 to 5 electron volts. Silicon has around 1.14 electron volts, whereas for gallium it is around 3.4 electron volts. They are widely used in electronics because they have versatile material properties and controllable conductivity. So coming to our main case, that is that what are crystals and how they are defined. So in 99% of cases they are solids that have perfectly repeating ordered atomic structures, and these materials have two major properties that they possesses. First, that they have periodicity in their structures, and second property is that they have ordered structure. So their structure is ordered and their structure is periodic. Like they can form cubic structures, they can form diamond structures, they can have a proper structure that has some order, and secondly they must have some periodicity. So after in an order structure, like in simple cubic structure, they must have periodicity, so their arrangement must be repeating in a certain pattern. Coming to some common examples of crystal structures, we can have we can like found crystal structures and crystal properties in salts like sodium chloride and magnesium chloride. Another example is quartz crystal that is used in watchmaking and time estimations. Salts are commonly considered crystal structures when they are in solid form. Uh, their general formula is metal plus halogens. Zinc oxide also has crystal properties when make a compound with atoms like gallium and indium or phosphate, which we will later on seeing in different applications as well. Now, coming to some major conclusions, or you can say hypotheses, that we are making at the moment before we indulge with the later deep discussions about the crystal structures and properties. We can say that a crystal structure describes how atoms are uh, actually arranged in a particular solid. Atoms organized in a repeating patterns, periodic, that are of course periodic and that are three-dimensional. So these particular structures are called lattices, that we will also going to discuss in deep discussion later in Max von Laue and Bragg's experiments. Common crystal systems are cubic, tetragonal, diamond, hexagonal. These uh, are some of the hypotheses that we are going to further prove in our later on discussions. If we say how crystal structures affect different behaviors of the semiconductors, so I would like to mention some of those behaviors. For an example, they affect the mobility, they affect the band gap, they affect the doping behavior, they affect the optical behavior, and also thermal conduction and device uh, device reliability factor also depends on crystal structures. In last, I would like to mention some of the behaviors of semiconductors as well, uh, with reference to crystals. So normally in our semiconductor studies, we will see diamond, cubic, zinc blende, or oxide structures. Uh, Before this, we have mentioned some of the properties of the crystal structure. So we have mentioned that crystals can be in the form of cubic, tetragonal, hexagonal, or diamond structures. So if we talk about the geometry that is commonly present in semiconductors, so that will be diamond, cubic, zinc blende, or oxide structures that we will be going to discuss in uh, later discussions, when we will be discussing hard X-ray diffractions and electrical diffractions of crystals. Later on we will be discussing these studies as well. So there we will be discussing zinc blende and oxide structures and geometries as well, that actually defines the behavior of uh, semiconductor materials. And these structures are uh, commonly developed due to the type of bonding and how they are actually grown up. So if we talk about future work, in our future work, that will be our future topics that we are going to discuss in our upcoming lecture, that is lecture number 2. We will be studying latest structures, for example diamond, directional, planes, and cubic structures in our lecture number 2. That will be more in depth in our crystal structures. Then we will be discussing some of the uh, techniques as well, to know about the structure, that will be Max von Laue and Bragg's experiment, and how their studies have experiment and how their studies and experiments are accurate in determining the crystal structures on a very minute scale. So coming to review of this lecture, in this lecture we have first of all have an insight from Reza Turkamani, and we have discussed his important work in the field of crystal structure and semiconductor materials. Then we have proceeded with the definition of semiconductor materials, that is presented on the screen, that what is a semiconductor material and how it is defined using metals and insulators. So then we have proceeded to another topic, that is crystals, how crystals are defined, and then what are the two main properties of crystals. That is number one, that is periodicity, and second one is orderedness in the crystal structures. Then later on we have discussed the important hypothesis that we are right now just mentioned as an information or as an fact, that uh, what are the possible crystal structures, what are the commonly found structures in semiconductors, and how they impact, or what are the factors of the semiconductor materials that are impacted by the crystal structures, and how they are grown. Thank you for attending this lecture. In our upcoming lecture, we will be discussing crystal structures, directions, planes, and some of the important studies in our upcoming lectures as well, from Max von Laue and Braxenbrack's experiments